Dear students, welcome to all of you. Numerical Practical number 26, RK4 method, Runge-Kutta fourth order method by C programming. Write a C program to compute the value of y at x equal to 1 by solving the initial value problem dy dx equals to 1 plus e to the power minus x square cos xy whole divided by 2 plus x square y plus y square log to the base e by RK4 method correct up to 6 decimal places, giving the value of y equal to 4 plus r minus 8 by 20 at x equal to 0. R is the last digit of your CU roll number. Runge-Kutta fourth order method, we consider first order differential equation dy dx equal to fxy with y x0 equal to y0. This fxy is linear, non-linear, and the formulas for Runge-Kutta fourth order method is yi plus 1, this equal to yi plus 1 by 6 bracket k1 plus 2k2 plus 2k3 plus k4, where k1 equal to h into f xi yi, k2 equal to h f bracket xi plus hi comma yi plus k1 by 2, k3 equal to h f of xi plus h by 2 yi plus k2 by 2, and k4 equal to h f at the point xi plus h yi plus k3. I runs from 0 1 2 up to n minus 1, and this is the formula for Runge-Kutta fourth order method. Now we come to this programming. Now first we define the function. This function f, arguments are float x and float y, return 1 plus exponential e to the power minus x square cos x into y whole divided by 2 plus x square y plus y square log x to the base e, natural logarithm to the base e. This is the floating variables x0, y0, k1, k2, k3, k4, and k, y, x, h, xn. Integer variable are, first we import the serial number r, last digit of your serial number r, enter the initial value x0, here x0 equal to 0, x equal to 0, x0 equal to 0, initial value of x is x0, and y0 equal to 4 plus r minus 8 by 20. So initial value of y0 according as r, value of r. Print the, enter the final value of xn. Here final value is y equal x equal to 1. So final value of x, that is xn equal to 1, put here. Enter the step length h, say 0.1 step length h, and then print this value of x0 and y0. Now x equal to x0 and y equal to y0. While x less than xn, k1 equal to h into fxy, k2 equal to h into f x plus h by 2, comma y plus k1 by 2, k3 equal to h f x plus h by 2, comma h y plus k2 by 2, and k4 equal to h into f x plus h, comma y plus k3, and k equal to k1 plus 2k2 plus 2k3 plus k4 whole divided by 6. Now new value of y equal to old value of y plus k, this k, and new value of x equal to old value of x plus h. Now print this x and y and return 0. This is the program. This is the program. Save, compile, and now run. Compile and run this program. Enter the last digit of your serial number, say 0, put 0. Enter the initial value of x0, say 0. obviously the initial value of y0 this is equal to 3.6. Enter the final value of xn equal to 1, say. Enter the step length h, say 0.1. So this is the table x and corresponding value of y for this initial value x0 corresponding y0, and the step length 0.1 and this 0.2, 0.3, 0.4, 0.5, 0.6 and up to 1. So value of y at the point y equal to 1, this is equal to 3.604197, and this is the programming. Now we back to this theory. Here the special case, this Runge-Kutta fourth order method is a special case. This Simpson one-third rule. Let fxy be a function of x only. Say fx. That is fxy independent of y. Then this k equal to 1 by 6 k1 plus 2k2 plus 2k3 plus k4. So obviously this absent the term y. So from this k1 is this k1 equal to h into f xi yi, so absent this yi, so k1 equal to h into fx, k2 equal to h into f of xi plus h by 2, and absent this term, and so k3 equal to similarly h into f xi plus h by 2, k4 equal to h into f xi plus h. We say this x this, and so we get k equal to h by 6 equal into fx plus 4 f of x plus h by 2 plus f of x plus h. And the initial value problem 1 given problem, so dy dx equal to fx with a condition y x0 equal to y0. So this dy equal to fx into dx, and integrating this, and from this range x0 to x1, that is x1 is x0 plus h, we get y integration y0 to y1 dy equal to integration x0 to x0 plus h fx dx. So obviously y1 minus y0 equal to h by 2 whole divided by 3 by Simpson's one-third rule for integration, numerical integration. This fx0 plus 4 into f of x0 plus h by 2 plus f of x0 plus h, because this x0 to x1 equal to h, so the midpoint x0 plus h by 2, so midpoint step mid step length is h by 2. So this is the Simpson one-third rule, and we get this equal to y1 obviously equal to y0 plus k, and k is this value of k by this above relation 2. So obviously we get this Runge-Kutta fourth order method is a particular case of Simpson's one-third rule when dy dx, that is fxy, be a function of x only. Now we give here a geometrical interpretation of Runge-Kutta fourth order method. Now we replace xi by ti for time variable ti for interest. We need the above equations and redefining kj, that is k1, k2, k3, k4 as follows. We get this yi plus 1 equal to yi plus h by 6 k1 plus 2k2 plus 2k3 plus k4. Now where this k1 equal to f of ti yi. Note that before we define k1 equal to h into f xi yi. So we here remove h. This h is multiplied by this h by 6. So k1 equal to, actually k1 equal to f of ti, why we redefine this k1. This is the f is the value dy dx equal to f. So obviously this k1 is the dy dx, this is the k2 equal to f, that is dy dx at this point ti plus h by 2 yi plus h by 2 k1, k3 equal to this function f, this equal to this, and k4 equal to this. So we get geometrically this point is y0, this t0. We interested for one interval, this t0 to t0 plus h, and this point is midpoint t0 plus h by 2. So k1 actually this is the derivative of dy dx, that is the tangent at this point y0. This is the blue color, in the blue color original value, exact value of this, that is equal to y equal to yx, and this is the exact value. By we are interested for the numerical value of this, so this is k1 at this point, and k2 is the value of dy dx, that is f, function f, at this point, this t0 plus h by 2. So obviously this is the y0, so k1, so this k1, this point is this height is from this y0, so obviously from this height is y0 plus h by 2 into k1, because this is the h by 2, and so this height is this h k1 by 2. So actually this point is obviously t plus h by 2, and value of y is this y0 plus h k1 by 2. So at this point, actually, this is the Euler's approximation of this point at this point t plus h by 2, and this point is k2. K2 is the slope at this point for t plus h by 2, k2. So obviously, this k2. So we draw a parallel line. This slope parallel line. This k2 is this, and we get this point. That this value is this correspondingly, and this k2 is the f of ti plus h by 2 comma yi plus h by 2 k1. So k2 is the actually this is function is the derivative, that is the slope at this point, ti plus h by 2 comma yi plus h by 2 k1. Here ti t0 and yi is y0. So at this point, this, so obviously this height, that actually this height is y0 plus h k2 by 2. This height is k2 by 2. This is length is h by 2, and correspondingly this height is k into h into k2 by 2. So this point is this, and next we find k3 at this point. At this point means this midpoints t0 plus h by 2 comma y0 plus h k2 by 2. We draw a slope that is the function value fxy, that is k3. So k3, so this is the slope at this point, and next we draw a parallel line through this point y0. So this point is this y0 plus hk3, actually this height, and correspondingly this point is t0 plus h. So this point, and then average height did this explain this. Here yi plus 1 is the rk4 approximation of y at this point ti plus 1, which is determined by the present value yi plus the weighted average of the 4 increment hk1, hk2, hk3 and hk4 with the respective weights 1, 2, 2 and 1. So the sum equal to 6. So we here this equal to yi plus h by 6 into k. This k1 plus 2k2 plus 2k3 plus k4 equal to k. So divide by the sum equal to 6, where the each increment is the product of the size of the interval h and the estimated slope specified by the function f. This is the function actually f tiy, actually the dy dx, dy dt, sorry, dy dt. So obviously this is represents the slope of at this point ti yi on this. Here we discuss the steps for the interval t0 to t1, actually t0 to t0 plus h. Here k1 is the slope, that is the approximate derivative at the beginning of the interval t equal to t0. So obviously at this point t0, and k1 is the slope of this functional. This is the blue curve is the function y equal to yx. So we draw a slope this at this point t0. K1, and y0 plus h by 2 k1 is the intermediate value of y at t equal to t0 plus th by 2 using the k1. This is the y0 plus this. So obviously this is the y0 plus h k1 by 2, and this point is this. So this is the value of y at this point for t0 plus h by 2. T0 plus h by 2. So we get this, this is the y0 plus h by 2 into k1. So for at this point k2, k2 is the functional value at this point t0 plus h by 2 comma y0 plus h by 2 into k1. So k2, we draw k2 is the slope at this point f of at this point over t0 plus h by 2 y0 plus h k1 by 2 at this point k2. So correspondingly k2 is the slope of the midpoint t0 plus h by 2 of the interval. And similarly y0 plus h by 2 k2 is the another intermediate value of y at t, that is t0 plus h by 2 using k2. And k3 is the again the slope of the midpoint T0 plus h by 2. T0 plus h by 2 at this point K3 is the slope at this point K3 at this point T0 plus h by 2 and y0 plus h by 2 into K2. So and y0 plus h K3 is the is an estimate of y at t plus T0 plus h using K3. So K4 is the another slope at the end point of the interval, that is t equal to T1, that is T0 plus h. So y1 equal to y0. So estimated value, that is the numerical value, and this is the this is chord. This last chord is the joining this average of this K1, K2, K3, and K4. This is the this the y0, this y1, this point, this T1 y1, this star point in green color. This star point actually the estimated numerical approximation by Runge-Kutta fourth order method. Actually, very small error up to order h to the power 5. So this is the this line for average weighted average for this. So this is the y1 is the Runge-Kutta fourth order approximation value for y at the point t equal to T1. In averaging the four slopes, greater weight is given to the slopes at the midpoint T0 plus h by 2, because this K2 and K3 at the slope of the midpoints, so we get the greater weightage, this 2 and 2, and this for the point T0 this 1, and the weightage is 1 at the end point, this K1. And this is the beautiful geometrical significance interpretation of this. And we from Wikipedia get this graph. Thanks Wikipedia, and hence is the Runge-Kutta fourth order method. The explanation from this actually spelling of this Runge-Kutta and this beautiful description of Runge-Kutta, and this is the graph from Wikipedia. And thank you for watching this video.